All right, friends, hello. Are there any questions from the weekend? Could you give me like a wave if you might have a question from the weekend? Yes. Oh, strong, yeah, strong acids ionize completely, yes. We'll go through that when we get closer to that, okay? So don't worry about it just yet, okay? Other questions from anything from the weekend? Okay, dokie. Then, in that case, we need to go up here and go to temperature, page 52. Oh, you have a question, yes. Isabel, did you have a question? No, okay. Okay, so we're on page 52 then. And I would like you, because it's worthwhile doing every single time, I would like you to please define Le Chatelier's principle. Write it down. Okay, so we know that it's not what you do, nature tries to undo, hopefully. So if that's what you wrote down, you need to try again. Yeah, you need to write it down. Because you might be able to say it, which is fine, which is a good way of reviewing, but if you cannot write it down, then you don't actually know how to define it. Yes? Page 52. When a what? System. What next? Yes. Yes, we're not going to say nature though. We're going to say the system will shift yes. Oh, when a system, yes, at equilibrium is stressed. Okay, what's wrong with me? I can't even conjugate my verbs. The system will shift in order to minimize the stress. Yes. What would you want to say? Move? Move is not a word that we usually use in terms of an equilibrium. We usually say, like, the word shift is just where it's at, you know? Yeah. All right, so we're going to look at Le Chatelier's explanation of shifting in response to temperature changes. In the reaction above, the forward reaction does what with heat? Releases. The reverse reaction absorbs. If we decrease the temperature, and we can use the arrows like we did before, if we decrease the temperature, the amount of heat in the system has decreased. According to Le Chatelier, the system will shift in the direction that does what with heat? Do we want to absorb heat or release heat? Think about it. Chat with your neighbor. Okay, so if we've decreased the amount of heat, that has been the stress. The system is going to shift to relieve that stress. So is the system going to want to release heat or to absorb heat? Yes, release heat. In order to bring the temperature back up. Therefore, in this particular instance, and if you want to, you can draw your arrow. Where would I draw my arrow? Would I draw my arrow here? Nope. Where would I draw my arrow? Above. And where should the arrowhead go? On the right, yes, because it's going to touch the tail of the other one, okay? So the system is going to shift right. So that would be a Le Chatelier explanation. You could also explain it in terms of rates. I would like you to do that just verbally to your partner right now. Explain that shift, that same shift upon the decrease of temperature in terms of rates. Yes. Yes. Shh. Yes. No, because the heat is released energy. That's what heat is. Heat is the motion of particles. Okay, so if it releases heat, the temperature is going to go back up because the particles are going to move faster. Does that make sense? Yeah. Okay, good question. Yes. That's without all the wordy words. Yes? That's just a bare bones. Okay? Now, I would like to have a quiz on properties of equilibrium, dynamic equilibrium, macroscopic properties, blah, 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 either Thursday or Friday this week. It's up to you guys whether you want it Thursday or Friday. Chat for 1 minute. I thought so. Okay, I'm not going to give you a whole minute. I'm going to give you 10 more seconds. Okay, Thursday. Friday. Okay, Friday it is. Okay, next, decreasing temperature. Now you can also actually use this phrasing. You can also use this phrasing if you wish to explain temperature shift in terms of Le Chatelier. Decreasing temperature favors the if we decrease temperature, what does the system want to do? The system wants to increase temperature. So what's going to increase temperature? What kind of reaction? An exothermic reaction will bring the temperature back up. So since it releases heat to bring the temperature back up. Increasing temperature, therefore, must favor the endo. Remember, now we're turning that motion energy into potential energy stored in the chemical bonds. Yes, since it absorbs energy and turns it into what kind of energy? Potential energy. It absorbs heat. You don't have to say this, but it's just for your own thought process. To bring the temperature back down. Do you guys think you could do a rate and concentration diagram for this when we decrease the temperature? Yeah, yeah.
temperature goes down, right? But you said that releases heat to bring temperature up, right?
Yeah.
So then what if this releases heat
Uh-huh.
as this, so then the temperature be going up?
Yeah.
Yeah. But you said the temperature goes down.
Oh, no, that's our stress.
Oh, the stress is the decrease in
The
temperature.
stress is the decrease in temperature. That
Okay.
make it better? Yeah. The decrease in temperature is the stress, not the shift. Okay? Why are you not erasing? You were erasing all the time before. Okay, there we go. Huh? Are you right? How are we feeling about that? Did I do it right? It doesn't matter. No, your starting positions might be different. Your finishing positions might be different. Yeah, as long as they're proportional and they're going up and down, you're fine. They don't have to cross, no. It just depends where you draw everything. If you drew NH3 at the top, like if this one, instead of being N2, was NH3, they would never cross because it would go up and the other two would go down, right? Yes. Shh. Yes. Yes. My diagram was just getting really cluttered. All right, we good? Nobody's saying no? Okay. Fill in the chart. Yes. You can check the answer up here if you want to for the first one. Let me know if anything confuses you or if I've done it wrong, which is always possible. Also, let me know if I scroll too quickly, okay? Okay, we've not done the demonstration in the tubes. We'll do that maybe tomorrow or the next day. Because they took away our tubes, but I can make it, so it's okay. Because they take away everything fun that we have in the world. Yes? Good? Cool. Yes? Why products are being made faster than reactants? Okay, because our increase in temperature increases the forward rate, the endothermic reaction, more than the reverse rate. The reverse rate increases, but not as much because it's exothermic. So we are making products faster than we're using them up. Did that make sense? Cool. Now, let's determine if a reaction is endo or exothermic based on what we see. So these are two gases. Gas, gas. One of the gases is brown. One of the gases is colorless. When we heat the tube, okay, why is this flippin' pen not doing its thing? When we heat the tube, it becomes a darker brown. Now, the question is the forward reaction endo or exothermic? See if you can think your way through it before you walk through the whole thing. So if we increase the temperature, it became darker brown. And I want to know, where is the heat term? If you were asked this on a multiple choice question, say, I don't know, you'd need a few more variables because you got to have 4 choices. But if you were asked this on a multiple choice section, the arrows would be a really good, fast way to figure this out, yes? Because you could say, if I increase the temperature and my kilojoules are on the right, then it would shift towards colorless, and that doesn't match what I see, yes? That means that the forward reaction must be endothermic. And you would just leave it at that because it's a multiple choice question. Yes? Yes. Could you have what? We don't, technically you can, but that's just a weird thing to do. Okay? Now, that being said, they will sometimes do that in like the old, okay, all my exams are from old provincials, and they will sometimes do that in the old provincials. So, but it's just a weird thing to do. AP will not do that. I can't see them doing it. Okay, so in increased temperature, when we increase the temperature, the system shifted to the, which way? It became darker brown, so it shifted to the right. So in terms of Le Chatelier, that would be in order to, we increase the temperature, therefore do we want to absorb heat or release heat? We increase temperature. Therefore we want to absorb that excess temperature, yes? I'm using heat and temperature interchangeably, which is completely wrong, but that's okay. If you think about it that way, for this kind of question, it's all right. Yes? Hmm? Yeah, probably. Yeah, probably. But, you know, seems likely. Okay, in order to absorb heat, to bring the temperature back down. Therefore, the heat must be in the reactants. Therefore, the forward reaction is endothermic. So you need to be able to do that kind of a question based upon what you see, which way did it shift, therefore which side is the heat term on. Yes? Okay. Exercises, excellent. We're going to move on to 2.2e. That is page 57. Okay, we're looking at the effect of a catalyst on the equilibrium position. Remember, a catalyst provides an alternate pathway with a lower activation energy, but it does it for both. I don't know why that line went there. Forward and reverse. Yes? Yes. Change in temperature will always affect the endothermic direction more. If you increase it, the endothermic rate will be increased more. If you decrease the temperature, the endothermic will decrease more. Now, a catalyst speeds up both rates by the same amount. Both rates are still equal and there will be no shift. So starting with an equilibrium and adding a catalyst, we can draw our new equilibrium arrows. The forward rate increases. What happens to the reverse rate? It increases by the same amount. So for our rate diagram, do you think you guys could draw it? Go for it. Super fun, right? Woo! Yeah, nothing happens. I'm just kind of showing you where. There we go. Oh, I didn't draw my line very well. Oh, well, that's okay. There we go. Now, although a catalyst has no effect on the position of the equilibrium, it does make you reach equilibrium faster. So if you just dump some reactants in there and you're like, how long is it going to take to get to equilibrium? It will happen faster if there is a catalyst. That's all. So if we start with reactants only, can you guys draw a rate diagram where we're starting with reactants only? We are not yet at equilibrium. Let me give that a try. Where should the forward reaction rate start? High. Where should the reverse reaction rate start? Low. That looks better. Yes. Is it zoomed in? Oh, no, we're already at equilibrium here. So this diagram does not relate to the other diagram. Okay, yeah. Now, what if we added a catalyst? What would happen to each diagram if we added a catalyst? It would be a straight line sooner. You would just get there sooner. Yes? And rather than me trying to draw this, I think if we're lucky, look at that. On the next page, yes, so we have the forward rate and then with the forward rate with the catalyst. So much better than I could draw, yes? Okay. There's our concentration diagrams. Now, your concentration diagram, can they cross each other? Yes. Can they not cross each other? Yes. It just depends on the position of the equilibrium. At equilibrium in situation A, would you say reactants are favored or products are favored? What is favored in diagram A? Yes. That's, these are concentrations. Yes? So that's the concentration of the reactants, the concentration of the products. There is no rate diagram here. Okay, neither of these are rates. This one's rate, this one's not rate. So in situation A, what does it mean if a side is favored at equilibrium? Yes? There's more of it, yes? Higher concentrations. So who is favored at equilibrium in diagram A? Products. And do you remember we had a term for the ratio of the rate, sorry, yes. Oh, that seems to make a lot of sense. Yes. Yes. So it should all be expanded. Oh man. So it turns out that we can draw a better diagram, but okay, here's the thing, you're never gonna have to draw that diagram, but yes, you're absolutely correct. Did you guys catch what he said? Okay, if you had a catalyst, your forward rate should be faster to start with, right? So it should actually go like this and like this, and I don't know. Anyway, the catalyzed one would all be higher because everything's faster, right? And they should both be equal but faster at equilibrium. Okay, good news. I would bet money that you will not have to draw that diagram, like from catalyst to non-catalyst, okay? It's just to give you that information, okay? All right, how about in this, oh, actually, before we go on, if products are favored at equilibrium, do you remember we had something called a K? It was a K, E, Q, EQ for equilibrium, and it is the ratio of the concentration of the products over the concentration of the reactants. If the products are favored at equilibrium, what can we say about the value of KEQ? KEQ is? Well, it's always going to be positive because your concentrations are always positive. So you have a positive number over a positive number. Yes. Because we have a bigger number over a smaller number because the products are favored, so KEQ is greater than 1. And I'm going to be more clever on this other one here. I'm going to actually draw my KEQ, where I have a KEQ where my concentration of products is small, and my concentration of reactants is big. That makes it a little more visual, right? And if that's the case, then KEQ, the value we can say is less than 1, because we have a smaller number over a bigger number. And that means that our reactants are favored. Okay, so there's the language in diagram A. The position of the equilibrium sits more towards the products. Therefore, we say it favors the products. In diagram B, the position of the equilibrium sits more towards the reactants. Therefore, we say that the system favors the reactants. Excellent. Okay. So, do catalysts affect the position of the equilibrium? No. Effect of an inert gas on the position of an equilibrium. Adding an inert gas, what does inert mean? Unreactive. For example, the what gases? Noble. To an equilibrium does not affect the concentrations of the reactant molecules. So if we have not changed the concentration, have we done anything to the rate? No. Therefore, the rates of the forward and reverse reactions are unaffected, and therefore adding an inert gas causes no shift. When adding an inert gas, neither rate is changed. Sometimes a helium atom will block a collision between reactant molecules if the helium gets between them, but other times the helium particles will cause a collision between reactant molecules as one reactant bounces off the helium and collides with another reactant molecule. Okay, you're not going to have to explain that, you just kind of need to have a general understanding of it. Inert gases do not affect the position of the equilibrium. Oh, look, you do not need to be able to explain this, but you should know that the inert gas has no effect. My goodness, aren't I clever? I think of the same dang thing every year, even when I'm not saying it. Okay, could you draw a rate diagram for this? So we're going to start at equilibrium. Yay! So friends, what's happening here? What's it gonna look like? Absolutely nothing happens, right? The most boring diagrams you can possibly imagine. Okay? Woohoo! Now this is going to become important in Unit 3 because in Unit 3 we look at precipitation and dissolution. Okay? Solids and liquids are pure substances. What can you say about pure substances and their concentrations? They do not have concentrations. They do not have concentrations. Why not? Yes, of course. Why not? Their concentration is just a constant. It's just their density. You cannot change it, so it will, if you cannot change a concentration, it will have no effect on the position of an equilibrium. Yes? So we can change the amount of solid or liquid in an equilibrium system and cause no shift. So here, let's look at a solubility equilibrium. This is for Unit 3. We have an ionic crystal lattice, and it breaks apart when placed in water. Now we're going to add some more. We're going to add some. We're going to add some more. And eventually, you can add more and more and more, and you stir it, and eventually there's going to be a pile of solid at the bottom. Yes? Does that make sense? Okay. Does the solid stop dissolving? Particles are bashing into the solid, so those bonds can be broken, yes? The water molecules can surround the ions and break them apart. So let's take a look at what's happening here. If we have a very small pile of solid, for every one particle that dissolves, what has to happen? This is a saturated solution. If it's saturated, no more will dissolve. So if it's saturated, if no more will dissolve, then every time one set of particles dissolves, what has to happen? Another set of particles has to come together and form solid, okay? So the rate of dissolving and the rate of recrystallization too big of a word, oh my God. Crystallization those two have to be equal. I'm just going to call it recryst, okay? Those two are equal. Now, I got a little tiny pile there, so I don't have much surface area. There's not much surface area. Tiny pile. Not much surface area. If there's not much surface area, what can you say about the rate? The rate will be comparatively small. Okay, so the rate of dissolving is slow, and the rate of recrystallization is slow, but they're slow and they are still equal. Take a moment, just ponder that. Yes? It still dissolves, it still recrystallizes, but every time we get one dissolving, another one has to recrystallize. Yes, yes, yes. Yes. If it's not saturated, the rate of dissolving will be greater than the rate of recrystallization as long as there is still solid present. Yeah, it'll shift until it becomes saturated. If you run out of solid before it is saturated, you won't have an equilibrium, right? Because there won't be any solid to go back and forth with. Yeah. So until a solution is saturated, you won't have an equilibrium. Once a solution is saturated, you will have an equilibrium. Yes? Well, I just was tired of drawing M's and X's, so I put them all at the top, but they would really be everywhere in the solution. Okay, so that water at the bottom, it also gave me some place to write. Okay, so plus it meant that when I did this, I could like cut and paste. So you'll notice that the number of M's and X's are the same for both places because I cut and paste the drawing. All right, now let's take a look at this one here. Now we have a big pile of solid. Yes? So I'm not just going to have one little particle coming off. I could also have that happening over here. Yes? So let's say I've doubled the amount of surface area. I've doubled the rate of dissolving. What have I also doubled? I've doubled the rate of dissolving. I will have had to double the rate of recrystallization. So we are going to have so if we have a big pile of solid, there is more surface area. Therefore, the rate of both dissolving and recrystallizing, because they both occur at the surface, I'm just going to call them fast. I'm not going to say faster. I'm just going to say fast. Okay, so we still have the rate of dissolving is equal to the rate of recrystallization. But in this case, we have a faster rate of dissolving and we have a faster rate of recrystallization. Yes? When we get to the solubility unit, people want to say, oh, if I add more solid, more will dissolve, right? They'll take a look and they'll be like, oh. And we add more solid and they think, oh, I've increased the concentration of the solid. Oh, look at me go. That means it's going to shift to the right. Except that, what? Solids don't have a concentration, therefore they do not affect the position of an equilibrium. You can put in solid, you can take out solid, doesn't matter. Once it's saturated, it's saturated. It cannot take more. It won't lose any unless you start like, you know, evaporating or something like that. All right, good stuff. There's a summary on page 61. If you're interested in that, I think if you understand it, you probably don't need the thing. Have my batteries died in my mouse? I think they have. That's okay. Oh, there we go. Ooh, forgot one. Feel free to read through this. We're not going to spend any time on it, okay? How much time do we have left? 10 minutes? Okay, in that case, why don't you guys do 2.2G? And maybe 2.2E? Or actually, is it 2.2D? 2.2D. I'll give you the page references. Pages 54 to 56. Hi. Of course. Hi. Hang on. Yes. 60, yes.
It won't go to 2.3, right?
No.
Okay.
Okay, friends, all of pages 67 to 90, it's just like practice, okay? You don't need to do it all. The reason there's so much practice is that my regular chemistry classes often have a great deal of difficulty with this. So I provided more practice than anyone could ever want, okay? There's one part where I'm like, tell me the story of what's happening here. I wouldn't actually write it all down. That would drive me crazy. I'd just kind of tell myself the story and then check the answer key and see if I did it right. You know what I mean? Maybe tell your friend the story and have them check the answer key, and then you tell them the other story. That would be like, I don't know, it's in here somewhere. There's just a freaking lot of extra practice. Next day we will be starting on section 2.3, which is not on Friday's quiz. Okay? 2.1 and 2.2 is Friday's quiz. Yes. Hi, I'm sorry I've been ignoring you.
No, that's all good.
Yes.
This is a random question.
Okay.
Right here. So, when you're talking about KEQ equilibrium constant,
Yep.
that is concentration of products over concentration of reactants.
Yes.
I assume it can't be negative. Because you can't have
No,
negative concentration.
that's right.
But can you have zero? You have no products.
No. Then it's not an equilibrium.
It's just right? Like,
It's not at equilibrium, right? Because in order to be at equilibrium, you need to have products turning into reactants and reactants turning into products. Both products and reactants have to be present, right? Right? Yeah.
Because I was like,
Because how could the
rates are
forward
the
rate
same.
equal the reverse rate if there's nothing to
But they're both zero. But
Yeah.
there's nothing else. Okay,
Yeah.
that makes sense.
Yeah.
So it's all.
Yeah, like some of the solubility equilibria, their value is like times 10 to the negative 54. Right? So it's like this thing is not one solve.
It's like,
But it's not actually zero. I mean, you can get a product to solve it every once in a while.
and then it can also go into positive stability.
It's a lot harder. Just, well, yeah, if you start going towards positive infinity, what you're going to end up with is reaction. It gets too high.
I've got my road test tomorrow.
Oh, and I should stop recording now. That'd be good.